Hello, I'm Cho Jung, and I will begin my presentation for Termproject 3. Photolithography is the process of drawing semiconductor manufacturing diagrams on a wafer. It necessitates three primary components: the wafer, photoresist, exposure equipment, and photomask. While photolithography encompasses 8 detailed steps, today our focus will be on the core 3 steps: photoresist, coating, exposure, and the development. The first step is photoresist coating, which process of uniformly depositing a photoresist layer of the required thickness across the entire wafer. To achieve high-quality fine circuit patterns, it is essential that the photoresist layer is thin, uniform, and highly sensitive to light. To accomplish this, a method known as spin coating is employed. The second step is exposure, where light is directed onto the photoresist to create the desired pattern. There are three main types of exposure methods. 1. Contact. In this approach, the mask and the substrate physically touch during exposure, making it less susceptible to light diffraction. 2. Proximity. Proximity exposure involves exposing the photoresist with a slight separation between the mask and the wafer, minimizing the defects. 3. Projection. Projection combines the strengths of both contact and proximity exposure. It includes creating a gap between the mask and the wafer and then using lenses to focus the light. Each of these exposure methods comes with its own set of advantage and disadvantage, and the choice of methods depends on the specified requirements of the photolithography process. The third step involves selectively removing the photoresist applied to the wafer by spraying it, thus forming the circuit pattern by distinguish between area exposed to light and those not exposed to light. In the case of positive PR, the unexposed area remains, forming the pattern. Conversely, in the case of negative PR, the exposed portion creates the pattern. ASMS photolithography equipment hardness lies through the LPP method. It achieves this by utilizing a CO2 laser to ionize tin into a plasma state. Subsequently, this plasma emits EUV light, a vital component in the photolithography processes. EUV light exhibits a unique characteristic. It is highly susceptible to absorption by conventional lenses. To overcome this challenge, ASML employs mirrors instead of lenses. This strategic choice allows for effective light reflection, preserving the precision of optical system. Notably, ASML has made remarkable advancements in minimizing reflectivity loss. This progress has played a pivotal role in making EUV equipment commercially viable. This represents the photolithography process for Case A. According to the research paper, in the case of SU8 with a high aspect ratio, negative PR was chosen due to its excellent chemical resistance and its capability to produce high aspect ratio structures. During spin coating, when the wafer's rotation speed is low, PR is applied in a thicker layer, allowing for thicker coating at slower speeds. In the photolithography process, projection was preferred to overcome the limitation of contact and proximity printing method. Despite the need for a substantial amount of light due to the thick coating, it avoids mask damage. Ultimately, following the development process, the desired PR model is successfully produced. In summary, negative photoresist is utilized in a slow spin coating process, resulting in a height of 150 micrometer. Following this, a photomask with a line width of 20 micrometer is used for projection photolithography. Ultimately, after preserving the exposed area and completing the deployment process, a photolithography with a high aspect ratio featuring a 150 micrometer height and a 20 micrometer line width is successfully achieved. This represents the photolithography process for case B. The choice of a 20 nanometer line width suggests a preferred for a microprocess. Negative photoresist was ruled out due to its property of increasing molecular structure size when exposed to light, making it unsuitable for fine processing. This represents the photolithography process for case B. The choice of a 20 nanometer line width suggests a preference for a microprocess. Negative photoresist was ruled out due to its property of increasing molecular structure size when exposed to light, making it unsuitable for microprocessing. The paper recommends positive photoresist for high-resolution fine processing, which led to the selection of positive photoresist in this case. Initially, a silicon substrate is positioned and spin coating is employed to form the FET on top of it. Subsequently, in the photolithography process, the choice of projection was made for the same reason outlined in case A, to mitigate mask loss and contamination. Finally, following the development process, the FET gate is successfully created. This is reference. Thank you.